Vitamin E cream is part of Dr. Atkinson's daily routine. So what are the advantages of using this on your skin? Well, the atmosphere contains radicals. Radicals are atoms, molecules, or ions that contain a lone electron. Now, lone electrons are very active. Electrons like to be in pairs. So this lone electron is looking for another electron to react with. So instead of it reacting with your skin, it will react with the vitamin E in the vitamin E cream instead. Clever, eh? Okay, so how is it possible for a radical to be an atom, molecule, cation, or anion? Well, just to recap, a radical is a species that contains at least one unpaired electron. That's indicated by a dot, often formed from high energy environments, such as superheating something or being shot with ultraviolet light, for example. And these unpaired electrons cause radicals to be very reactive. Electrons like to go around in pairs, they're more stable. So lone electrons are very unstable. So let's look at some examples. So let's start with radical atoms. The kind of classic one is the chlorine atom. So chlorine has 17 electrons, 2, 8, 7. And so knowing that, you can see on the valence shell, there's 1, 2, 3, 4, 5, 6, 7. There's a lone electron there, and that's what makes it a radical. Now, that's not to be confused with a chloride ion. The chloride ion is 288. That has 1, 2, 3, 4, 5, 6, 7, 8 pairs of electrons. Note that you can do lines, and those lines represent a pair of electrons. That can be 2 crosses, 2 dots, as you like. Alrighty. For molecules, the classic one is the OH radical. So let's just work out the Lewis structure for that. 6 valence electrons for oxygen, 1 for hydrogen, divide by 2. That gives me 3.5 pairs of valence electrons. So 3.5 pairs. I'm going to put 1 here, 1 here, 1 here. That's 3. And then bop, there's the lone electron there. So that is called the hydroxyl radical. Hydroxyl radical. Again, not to be confused with hydroxide. Hydroxide, that's not a radical. 6 valence electrons, 1 there, plus a cheeky extra 1. So divided by 2, so that's going to give me 4 electron pairs. So if I wanted to draw the Lewis structure for that, there we go, no lone pairs there. So hydroxide, that's wrong. We're just sticking with the hydroxyl radical. The other one that seems to be popular in the books is the nitrogen monoxide. So nitrogen has 5 valence electrons, oxygen has 6 over 2. So that's going to give me 5.5 electron pairs. All right. So I've got 1, 2, 3, 4, 5, and half an electron pairs an electron. So that's the nitrogen monoxide radical. Now we could be cheeky and we could maybe ask you, well, hold on, couldn't this be the nitrogen monoxide radical? Both of them fit the Lewis structure rules. Well, you'd have to use formal charge to check that out. So let's quickly do the formal charge. So formal charge, nitrogen has 5 valence electrons. And my way of doing the next bit, instead of learning that horrible equation, is how many electrons are in that circle? 1, 2, 3, 4, 5. So 5 minus 5 is 0 formal charge. And now for the oxygen, I've got 6 valence electrons in oxygen. Let me draw a circle around oxygen. 1, 2, 3, 4, 5, 6. 6 minus 6, so that's 0. So that's looking good. Zeros win the formal charge. Let's just double check on the other one. So I've got 5 minus, how many electrons are in that circle? 6. So the formal charge is minus 1. And over here I've got 6 valence electrons. How many electrons in that circle? 5. So it's plus 1. Yeah. So this is the preferred structure here. Zeros on formal charge is the winner. Okay, so cations. So I think of plusy cat. Plusy cat. Cations are positive. So taking a little detour, When you were using the mass spectrometer, well, not using one, I've never used one myself, they're expensive. In order for things to go through the mass spectrometer, they have to end up being positive. So that's abundance. And maybe you haven't done it yet, maybe you will do it. There's always, at the maximum M over Z level, is what's called the M plus, the molecular ion. So molecular ions are actually cations that are radicals, since we're talking about radicals. So for example, if I was to shoot ethane through my mass spectrometer, in order to make it positive, I have to knock off an electron. So rather paradoxically, the way that they knock off the electron is they actually shoot it with electrons, and the electrons knock off other electrons. And so once the electrons hit it, it becomes positive. It loses one electron. Now you can put a dot here and a plus. That looks a little weird, but that is the new IUPAC way of showing it. Frankly, in IB, normally they just leave the plus. But they've never asked a question about this cation radical. And for the anion radical, so that's going to be a negative radical. Well, that's a very obscure thing. I've never heard about it before. The textbooks aren't clear. But essentially, the one that seems the most common, if you get benzene and then you throw in a bit of potassium, you know potassium has 281, it has one valence electron. That valence electron can actually jump over to the benzene and it can squeak in, even though we've told you there's no more room. Apparently there is. So once that squeaks in there, you've got a positive potassium and you have a benzene radical that has a dot and a negative sign. The dot means there's a lone electron somewhere wandering around, and the negative, well, that's just a charge on it. Whew. I'm not sure what questions they're going to ask. This is all kind of new stuff. The most common place to find radicals in IB chemistry is when ultraviolet light breaks up chlorine, producing radicals, and then that reacts with ozone, producing more radicals. The chlorine radical can also react with an alkane.